let's start the new article, phasor method. So what is the actual meaning of this phasor method? In this chapter, the advantage of this method is in the addition of the harmonic function So which kind of functions you are considered as harmonic function? So for example, I am giving you a current as a harmonic function with a magnitude Im and the angular or the phasor quantity omega t plus delta. So this is equation number 1, and such kind of function is known as harmonic function because it's consisting of magnitude as well as this phase. Now to add the magnitude is very easy, but in order to add this angular quantity or the phasor quantity, the use of phasor method is arrived, and so I am starting the analysis by putting this harmonic function into the two-dimensional plane. So here I have put it in the xy plane this harmonic function I by drawing the Im magnitude on this side and the angle or with the angle omega t plus delta, which is at x plane. Now some observations which you have made from this graph. So the first observation is the phase omega t plus delta and here the delta is nothing but the phase difference is changing with time. Also, when this angle is changing with time, so with respect to origin O, the magnitude of Im will also change. Due to the change in the phasor quantity, and so the vector drawn in this figure is not steady. Suppose I am giving this point as name P. So OP vector, that is the position vector of the maximum current Im, is not steady because it is changing with time, and so I can make one assumption that the OP vector means the value of Im is keep on rotating in xy plane, but it rotates with what? It rotates with angular frequency omega. So such a vector means OP vector is called the rotating vector. And such kind of rotating vector is also known as the phasor or you can say the rotor. So instead of using the name rotating vector, you can directly substitute the name as phasor or the rotor. Now the vector which you have chosen over here, the harmonic function I is the scalar. But we are only representing the vector I, means the maximum value of Im as either rotating vector or rotor or a phasor. And now we will make the second assumption. The second observation is in this way. The harmonic function what you have considered is at a particular time t is equal to t, as you can see from this value. And so this gives us the instantaneous value of I. And here the instantaneous value of I we can also obtain for different time intervals. For time t is equal to t1, I can give the harmonic function as I1 is equals to, or we can say the value of I in this way, I1 cos omega t plus delta 1, and the other harmonic function. See, this time I have not get any subscriptal change because as the phase difference is changing, the value of omega t will also change, and similarly the value of I is also get changed. And the value of harmonic function I2 I am writing over here as. Now, if you want to get addition of these two harmonic functions, then what happens? Then we should draw phasors of all the function at time and then taking their x component. So first of all we have to get addition of their magnitude and then we have to add their y component. So it is basically given by the vector sum. And what was the theory of vector sum? So it can be done by drawing phasor for all functions at given time and then consider these as your x-axis. Now this is the scalar and now you can add all the functions, means a simple addition as you are performing in algebra. Similarly, the third observation what you have made in this graph, there is one more advantage of this method. If we take y-axis or y component of this function, that is cos of pi by 2 minus omega t plus delta. So here pi by 2 is given for the y component, that is the phase difference between x and y is pi by 2. And this particular function or component will result into sine omega t plus delta. And thus by considering this y component, we can also deal with this sine function. So this is another advantage. At the same harmonic function, we can consider with cosine function as well as the sine function by just represent the phasor of all the functions. Now we will start our analysis by consider two different harmonic functions, and that I am giving the observation as number 4. Suppose the two harmonic functions are I1 is equal to I1m cos omega t plus delta 1. Similarly, I2 is equal to I2m cos omega t plus delta 2. The arrangement of these two vectors are shown in the xy plane, which you can clearly see that I1m and I2m are connected by the use of the vector addition by the method of triangle. Similarly, over here, to find out the resultant function, vector I1m and I2m are connected by joining the tail of vector I2m with the head of vector I1m, and from this we can find out the resultant vector, or first of all we have to find out the angle between two vectors. And here the vector is representing the harmonic function, that is the two rotating vectors I1 and I2 is, you can directly find out. Here is the angle omega t plus delta 1 and here there is an angle omega t plus delta 2. So, the phase difference between them is delta 2 minus delta 1. And now, the resultant vector I am writing over here as, it is denoted by Im. So Im, and now I am getting a square because it is actually I1m plus I2m. So let's write down first of all with the simple value. Im is equal to I1m plus I2m. So applying square on both the sides, we will get Im square is equal to I1m square plus I2m square. And in the description of this figure, you can also write down that the OA vector is I1m, AP vector is I2m, and the resultant vector OP is Im, and that we are going to find at present. So it is the simple a plus b whole square example or expansion. So 2I1m I2m cos, here the angle is delta 2 minus delta 1. And here I am considered that the phase difference between two rotating vectors delta 2 minus delta 1 is simple delta. And so I will get the resultant harmonic function of current Im square is equal to I1m square plus I2m square plus 2I1m I2m cos of delta. Thus, this is the function, or we can say this is the resultant function, but we should remember here that the magnitudes of the vector of I1 and I2 and Im are I1m, I2m, and the magnitude of Im is represented by capital I. But here we have taken a simple Im, and with this our phasor method is over, and the resultant sum or the addition of two harmonic functions has been done within this theory. Now we will see the applications of phasor method in the AC circuit.